Hello and welcome to this multi-part series on control fundamentals. Today I'm going to be reading through the Honeywell Gray Manual, which the URL will actually be in the posting, but you can download right here. Now this manual is actually what I taught myself HVAC and controls from when I first moved into the field. There's not a whole lot of great reading around controls fundamentals. There's a couple things, but a lot of it is just so complicated that for a person who doesn't understand, is trying to figure it out, it doesn't really make sense. I found that the Gray Manual is simple enough that even if you have absolutely no background on HVAC and only understand basic math and maybe basic chemistry, basic mechanics of systems, stuff like that, then you should be able to pick up everything you need to know, at least to walk into a job and say, hey, I can understand fundamentally what is going on in this facility. You may not be able to program it, you may not be able to go and fix it, but fundamentally you'll understand what is happening within the facility. So I'm going to assign a chapter each week, and the chapter is going to have a follow-up video. That video is what we're going through right now. As you can see, I'm starting right here on what appears to be page 4, actually page 5, of the Controls Fundamental, the first chapter. It gives some basic definitions. I'm going to save you the boredom of me reading through definitions, but we're going to move right into what is this chapter telling us, why is it important. For example, if you were to look at this, what is this telling me? Well, we can see right here that this is telling me that I have a steam heat exchanger. We see the steam right here and we see hot water, and I can tell that I've got a process variable of outdoor air is going into a reset schedule between 0 and 60, and the corresponding temperatures of that reset schedule are right over here on the hot water set point. So I see 0, I get a set point of 190. You can see that since I'm at 30 right here, let's do some basic math, 60 and 60, so for each degree I get a 30-degree inverse effect. So if I go up a degree, I go down a degree here. Since I'm at 30 degrees, I go up 30 here, I go down 30 from 190, that gives me 160. That set point goes here. I'm getting feedback from my temperature sensor. It's coming here right into my controller. My controller's outputting a 41% command to the valve. The valve's allowing steam to go through. And right here we can see that my heat exchanger is supplying 159 and returning 148. Alright, so we know a lot from this valve, or from this drawing right here. We've seen a lot of the fundamentals of a closed circuit loop. It's not an open circuit loop, it's a closed circuit loop because you have a complete circuit right here. Alright, so moving in, we're looking at a picture of the building envelope. And it talks about the envelope of a building and what's going on. Now right here we're seeing some fundamental things. Your chiller and your boilers in the basement. Or if you're in Texas like I am, sometimes you'll see your chiller outside or in a mechanical room along with your boiler. You typically see cooling towers on the top. That allows the easiest way for it to take the draft effect, as well as it allows you to go and take advantage of certain thermal properties that we'll get into when we move through cooling towers. The intent today is not to break out every single system, because we will move in to every single system as we move through this series. The intent today is to give a fundamental overview. If you were to watch one video in this series, this one video right now would give you a fundamental overview of controls, enough that you would be able to understand if you're sitting in a meeting doing a job site review, or maybe you're an owner and you're trying to figure out what the heck is that controls guy talking about, and how is he justifying that he's 4 weeks late on delivering this project. Well, if you understand what you're saying here, if you understand what you're reading here, maybe that'll help you understand why you're getting told that a project's going to be late or you've got an increase in cost. Alright, so we go right through here. That's our basic building. It talks about a couple different types of control loops: ventilation, cooling, a fan loop, heating. It talks about, just some descriptions. This is basic general fluff. Really, you don't need to know this. Now here's a pretty interesting one. We talk about two concepts that are pretty important here, and that's infiltration and exfiltration. Typically a building ideally is wanted to be positive. What does that mean? That means that air is not coming in, rather air is going out. So if you're to open a door, you'd want to feel a slight breeze leaving the building. What does that do when a building's positive? Well, that's going to keep this firm thermal infiltration, ideally from these winds that we're seeing, from different outside pressures, from coming into the building. You know, if it's 100 degrees or if it's 20 degrees outside, we want to keep what's called our envelope. That's this exterior of the building. We want to keep our envelope positive. We want to keep our pressure positive, so effectively we're creating a bubble and we're keeping pollutants, allergens, things of that nature from entering the building, but we're also keeping thermal gain or thermal loss from the building. Now we see here we've got some ventilation that may be leaving. That may be in the form of an exhaust, because in order to keep our building positive, we're going to pull air in, but at the same time we've got to let air out because we can't have it too positive. We don't want to be blowing open doors. I'm sure you've been in an office building where you can't open a door because the building's too negative, or where you can open a door because the building's too positive. Now here's just going through some temperature concepts. It's looking at your BTUs, your heat transfer coefficient, just kind of explaining how long would it take to transfer air. Now there's a better equation, quite frankly, that's in the CEM manual, where it goes through the actual insulation ratio, and it'll take into account both, like for example, brick, sheetrock, your different R series insulations, things of that nature, window types, and it takes into account that. An engineer will typically plug that into like an eQuest or train trace model, and that'll actually give a calculated gain or loss from that building. Now we're going through into the heating equipment. Now heating equipment's pretty important up north. Down where I am in Texas, you don't see heating equipment as being that important. Granted, we do get some cold days, but majority of our time is spent either cooling or dehumidifying. So what we're looking at here is right here we've got a unit heater. You've seen these in loading docks. A fan, it's got a radiator, you've got some steam or hot water, maybe you've got an electrical coil, and the fan turns on and it's going to blow through here. And the thing with heat, whenever you see like a VAV box that's heating, or maybe you see, and let me see if I can draw a little picture here. Alright, so right here we've got a VAV box, okay? There we go, there's our box. We've got airflow coming through, and here's our damper, and maybe here's our heating coil. Let's just call that a coil. I know it looks more like an averaging sensor. Okay, now it looks more like a coil. Alright, so our damper's right here, and the airflow is coming through, and our damper throttles the airflow. Now whenever you're heating, you want to slow down your flow, and that's because of thermal gain. Here's an experiment. Go into your car, turn on the air conditioning in your car, and turn the fan up to full speed. Then turn the fan down, and as you turn it down, you'll notice the air starts to feel colder. And the reason it starts to feel colder is because the slower the air, the more effective the change is going to be. So when you're taking BTUs out or you're introducing BTUs in, you're going to notice that whenever the air is slower, you're going to have effective transfer. Now here's the thing. Typically, for cooling, the method we do is we introduce like between a 55 to 65 degree air, and you rely on air changes. And the air changes are going to change that temperature because your heat's going to kind of float to the top, your cold air is going to settle on the bottom, and you're going to change the volume of air. Maybe you're looking at 6 to 8 air changes. Maybe you're in a hospital, you're looking at 20. But you're changing the volume of that air. That one keeps particulates and pathogens out of the air, but it also helps cool a space down. Now when you slow down the air, naturally you're going to adjust your exhaust, so you're going to have the same air changes, but that slower air is going to get a better exchange from heat because you're introducing BTUs versus taking BTUs out. I know, wonderful picture. It doesn't look anything like a VAV box, but that's okay. You're not here for my art. You're here to learn about HVAC. So here we see, a grid panel. Maybe this looks like a panel that is sitting underneath the floor. I've seen both types where they put some copper tubing or maybe some stainless tubing, typically copper though, and they put this tubing underneath and then they pour a slab on top of it, and this becomes what's effectively called radiant heating. And it heats the floor because the floor mass in a large space can have thermal gain or loss. You can experience this by walking into an office that's been in a cold office all day. The office is warmed up, but when you touch your actual desk, your desk feels pretty cold. And that's because the I can't even pronounce the word, capacitance, which I don't know if we're going to cover today, but we will get to it. The capacitance, the ability to hold BTUs, is actually more in certain materials than others. For example, a wood can maintain more than a piece of metal. Metal will get really hot or really cold, and wood kind of stays a little more neutral. Now, that's not the exact technical term. It actually, the way the molecules are, the way it takes heat in, is different based off of the material type. Now here we're seeing some more things. We're seeing right here, we've got a thermostat. Now this isn't typical. We don't typically have a thermostat going right into the valve. We have a thermostat going into a controller that has an input to a valve. That then goes and controls the coil. The coil controls off of a discharge air zone temp, and that would be what we would see. There's a unit ventilator. These are, I like to call them classroom units. We all remember them going to school, that wonderful gray unit that if the teacher wasn't looking we could sneak over and change the temperature on because it was always hot. These things, I don't particularly like them, but they're still in use all over the place. They serve a purpose. You've got some outdoor air, you've got some return air, it mixes, comes in, goes through a series of coils and blows out the top. Here we're seeing some convection, we're also seeing radiant. Now, convection heaters, we've all seen them. They're traditionally, you'll see them in commercial, office space, government buildings, lining windows. You see this more so up north than you do down south. And this has a common loop, and it feeds through here. Typically, you'll have like a wax valve, and that wax valve will let the actual flow go through. Sometimes you'll have an actual control valve, and that'll be linked to a common thermostat. Infrared source, this is usually like some sort of metal, stainless, or something of that sort with an infrared heat source. Kind of reminds me of those giant heat rays that you see over your food whenever you go to a deli or something. You'll see that actually going and heating. It's radiating the heat. Hence it's called radiant heat. And convection is called a convection heat because it allows the air to flow off and it convects into the air. I know that's not a super technical term, but you get the point. Cooling, well, if heating is adding BTUs, and this all goes into the refrigeration cycle and into the cycle of heat and cooling, you're either adding BTUs or you're taking BTUs out. Cooling, you're taking BTUs and you're transferring them. And this sentence right here kind of describes it. Both sensible and latent heat contribute to the cooling load of a building. Heat is sensible when heat is added to the conditioned space. What does that mean? Okay. Sensible, right? That's just adding BTUs. Like moisture's added, etc. Right? So there, the humidity space, you must take the humidity out, right? Now, that is your sensible, and latent is an actual change. That's an actual state change. So you can have, for example, if I convert steam to hot water, I can have a lot of BTUs because I'm doing a latent change instead of a sensible change. Alright, so let's move into cooling equipment. Oh wow, doesn't this look similar? Yes, if you've mastered a hot water valve, you can understand a chilled water valve. The big difference is hot water valves, they typically control between 90 to 140. Electric heat coil may get up to 160, 180. Chilled water coils typically control to, if you've got a 42 degree supply, I mean, ideally you want a 55-degree discharge. When you're talking fan heat gain, you're looking at a 50 to 52 degree discharge off a chilled water coil. Now here, you see this kind of makes sense. Right here I've got a coil and it's coming through, and this is essentially a three-way coil. You can either go through or you can bypass. Here we've got some sort of refrigerant. This is typically what you see on what's called a DX direct expansion. The refrigerant is going to be compressed to a liquid. It then goes through the DX, it expands to a gas, and then that gas is then compressed, cooled down to a liquid, and that is how you take the actual heat out, because the state changes. Because remember, let's go back here. We can take a lot more BTUs out during a state change than we can an actual temperature change. I don't have the numbers in front of me, but steam is, or gas is somewhere around hundreds of BTUs. Water is in the single digits, if I remember correctly, and air is, I think it's less than 1. Now, I haven't memorized these numbers. Why would I memorize when I have Google and I can just go look? But to that point, just know steam is large, and I mean, then obviously you have phases above steam. But the point is we're taking advantage of that latent change. It's the same thing you'll see when we move into cooling towers. We take advantage of a latent change, and that allows us to remove massive amounts of BTUs. Take advantage of the fact that refrigerant changes states at different temperatures. For example, when it compresses to a liquid and evaporates to a gas, those are at different thresholds based off of the refrigerant types. So that allows you to do things. Pause. Okay, so where were we here? We were talking about our cooling. Now we're moving on to dehumidification. Okay, so dehumidification essentially is taking the humidity out of the air. Alright, seems pretty simple, right? I mean, you take humidity out of the air, and the air is going to be less humid. But what is humidity? Well, humidity is moisture being in an air. So we're not going to cover psych charts in this series, but essentially if you were to look at a psych chart on the left, no, it's too far to scroll down. If you were to look on it on the left, it would show grains of water per pound of air. Essentially, humidity is the amount of water that is in a pound of air. So what's going on here is you have air that has humidity, has water in it, and as we know, water contains more BTUs than what? Than air. You should be saying air. So if water contains more BTUs than air, then to take that energy out, we're going to have to use a fair amount of energy to conduct a state change, right? Because we want to take that energy out of the air, and we want to basically take air and solidify it into a liquid. Well, I guess not solidify, condense it into a liquid and have that liquid come out. So how do we do that? Well, we do that by lowering the temperature. What that's going to do, and we're not going to talk right about this granular bed absorption unit right here. We're going to talk about how it's done in most cases, which is through a chilled water coil with some reheat. Okay, so what happens is that the air goes through the chilled water coil. The cooling then, let me see if I can draw you guys another wonderful picture here. Okay, so we've got our air handler, we've got our cooling coil. Oh, come on, here we go. We've got our cooling coil, and we've got our heating coil. And heating, we're going to make with an X. And we've got a fan right here. So what's going to happen is our humid air, let's say, it's 80% humidity because we're bringing a lot of outdoor air in. And that's going to go through, This cooling coil is going to be around 50 degrees on the cooling coil right there. So as we move on the psych chart towards the colder temperature, our relative humidity bands right here are going, we're going to be essentially moving across a relative humidity. So we're going to be moving towards a greater and greater relative humidity until we reach what is called saturation, which means that as the air cools down, the molecules slow down, there's less room in the air to hold the water, and what's going to happen is that water is essentially going to fall out into the condensate drain, because we call water that's falling off of a coil condensate because it's condensing. The water in the air is condensing, so it's condensate, and it runs down the drain, and humidity leaves the air. We warm the air back up, so we're moving along this humidity chart, and then we warm the air back up, and lo and behold, we're at a lower humidity point. This will make complete sense when we move through the psych chart, but you're just going to have to trust me on it right now. Alright, humidification. Well, that is the opposite of dehumidification. So dehumidification aims for around a 50, 55, 60% humidity depending on your temperature, as we'll see in the psych chart section. Humidity, however, you want to be, now it says between 30 to 60%. Let's be real. You want to be around 40%. That's the general average. Below 30, you get static electricity, wounds start to dry out. It's just nothing good ever comes below 30% relative humidity. So with that being said, yes, there are some rules where you would want below 30%. There's always an exception to the rule. In this case, though, we're saying between 30 and 60%. Ventilation. If you haven't picked up on it by now, ventilation's how you provide airflow to a space. We've got a couple concepts. You've got what's called air changes. That means the amount of times that the volume of air in a space changes in an hour. So you hear like, I need 22 air changes in a clean room for a hospital. And that means I need to change the air 22 times. And maybe here I need 8 changes. That means I need to change the air 8 times. That entire volume of air through supply and exhaust changes. So what's going to happen is you're going to have air come in, air goes out. You have a couple different ways of this working. You've got a volumetric match, so the same amount of air comes in, same amount of air goes out. You've got a volumetric offset, which means a larger amount of air comes in than goes out. That creates a positive pressure. If more air goes out than comes in, that creates a negative pressure. Some spaces you want to be negative, some spaces you want to be positive. For example, an infectious room. You don't want that to be positive. You don't want to be blowing that crap all over the place. You want a negative room so that it sucks stuff in. And then once again, in a clean room, you may want that to be positive. Some places use what's called 100% outdoor air. What that means is affectionately called a single pass unit, meaning that you take all the air in, it passes once and goes out. That would be in a situation like an animal lab, where you don't want to circulate air. You want to take it in once, pass it through, and then go straight out. And you're going to achieve your air changes by simply varying the amount of supply versus the amount of exhaust. Now we talk through here, this is a mixed air solution. This is where air comes in, you mix the return air. Here's a nice little calculation for you. If you were to take your outdoor air damper position and your mixed air damper position, and you were to take your return air and your outdoor air temperatures, you'd be able to calculate what your mixed air temperature is. Filtration. Now there's a couple different filters. We see pleated, we see bag filters, you've got mechanical filters, you've got all sorts of things. You've got what is called HEPA, high efficiency particulate air filters. You see those a lot in healthcare, clean labs, etc. And then some cases you've got what we call essentially ultraviolet filtering, which you've got an ultraviolet light and it's supposed to kill whatever's in the air. Like, you don't want to get stuck inside an air handler with one of those lights turned on. It's really bad. And what that does essentially is that is going to kill what's in the air. And finally, the next one, as we're discussing here, electrostatic filter. Now this causes whatever's in the air, and you can actually see these a lot in houses. What'll happen is it'll cause the particulate to change its electronic value. we're not going to really get into that, but basically it'll charge the metal surface, and then certain particulates that are negative or positive will be attracted to it, and then you come in and you clean your panels every once in a while. Alright, it has been 24 minutes and we did not get through the first chapter. We are now on control system characteristics. Now, for the sake of time, because I know most people won't watch this if it goes past 30 minutes, I'm going to stop here. So if you're reading along in the book, you will want to have read all the way to, I found the page 15. And page 15 will begin when we do the next series next week. We'll go from page 15 all the way down to, I think it's page 28, but let me check. I was close. We will go to page 30. That will be next week. So thank you very much for watching this. I hope you learned a lot. I'm not a big fan of graphics, so if you're wondering where the graphics are, well, they're in the book you should be reading. I am a big fan of taking all of this language, condensing it in an easy way, easily understood format, so that you can learn in just real-world, day-to-day speak what you need to know about the fundamentals of HVAC. So thanks for watching.